All right, let's look at the second part of Chapter 1, Section 1. Now that we know what a set of numbers is, we can classify real numbers by their subsets. We can put a number and identify all the subsets that it belongs to. Let's talk about defining our own sets. If we want to talk about a set of numbers, we can define for our own self what numbers we want to talk about. But we have to have a way to relate that definition to somebody else. So we're going to talk about how we can use roster notation, interval notation, and set builder notation to let other people know exactly what we mean when we say our set of numbers. Let's talk about roster notation first. When I look at roster notation, the way that we write a roster notation is by using two what we call braces. We're going to open it with a brace and we're going to close it with a brace. And in those braces, all we're going to do is list every member of every element of the set that we're talking about. And it's called roster notation. We can think about it as just like we think about the roster on a team. If I have a baseball team, let's say that I'm building a baseball team and I've only got 4 players right now. And as I'm building my baseball team, my 4 players that I have right now, I've got Bob, I have Jamal, I have Isabel, and I have Sam. Well, the set of baseball team members that I have is listed in this roster. This is roster notation. I have 1, 2, 3, 4 elements: Bob, Jamal, Isabel, and Sam. And all I need to do is list each of the elements in between these 2 braces, and it defines a set for me. So if I wanted to have a set of numbers that included only 2, 8, -9, and 0, I would open with my brace, and typically speaking, we're going to write our roster notation from least to greatest value. So I'd write -9, and the next one is 0, 2, and then 8. So now I've defined a set with 1, 2, 3, 4 elements, and those elements are -9, 0, 2, and 8. So that's pretty straightforward. Well, let's talk about natural numbers now. Is there a way that I could write all the natural numbers in a roster notation? So the first thing we need to ask ourselves is, how many natural numbers are there? There's an infinite number. And if you think back to the previous lesson, the natural numbers, or counting numbers, are the first ones we learn. Starts with 1, and then 2, 3, 4, and it goes on forever. Well, in a roster notation, I could write a set with an infinite number of elements as long as it continues in a similar fashion. Here I added 1, and then I added 1, and then I added 1, and the dot, dot, dot implies that it will go on forever, adding 1 every time. So this is a correct roster notation for the set of natural numbers. Well, let's say I wanted to write the natural numbers from 1 through 3. Again, I'd open with a brace, and I would start my list. Well, what numbers am I talking about? I'm talking about the natural numbers, so no decimals and no zeros and no negatives, from 1 through 3. 1, 2, 3. That's the end, so I would close my roster up with another brace. I've got a 3-element set consisting of 1, 2, and 3. Now, let's say that I wanted to make a notation that represented all numbers from 1 through 3. Well, I could start my roster this way. See what we can do with the roster notation. If I write 1 where I'm starting at, and then if I'm going with all numbers, I need to include all the decimals and everything. So what do you think, 1.1? Well, what about 1.0? Well, wait a minute. What about 1.001? And well, how many numbers are there from 1 to 3? There's an infinite number. But they don't increase like this in a nice regular fashion. There's an infinite number on an interval between 1 and 3. I can't put all those in a roster notation. There's no way for me to represent it accurately. there's an entire interval I need to account for. So what are we going to do? We're going to use the uniquely named interval notation. So we can think back and we'll use all numbers from 1 through 3 again from the previous slide. And if you remember, you used to do number lines in Algebra 1. And on a number line, it goes on forever in both directions. If I wanted to represent elements on an interval, we could show it on a number line with the endpoints. We'd have endpoint 1, we'd list our endpoints in 3. If I want to go from 1 through 3, I'm going to include both those endpoints. If I want to include the endpoints, I make a dark circle, and then I connect them. That's not too bad. And we could write this as a compound inequality. We could relate the number line and the all numbers from 1 to 3 as a compound inequality. 1 is less than or equal to x is less than or equal to 3. Well, when we write our interval notation, we're going to do something very similar. We're going to write both of our endpoints, start with the lowest endpoint first, start at 1, and we go through 3. So we go 1, 3. We have our two endpoints written out here. If I want to include 1, which in this case I do, I'm going to put a bracket around it. It's kind of like it's holding it. It is including it. And I wanted to include 3, so I'll put a bracket around here. So my interval notation consists of a bracket, 1, 3, close bracket. And these brackets indicate that I want to include my endpoint in the interval. Include the endpoint in the interval. Now, let's look at the next one down here. All numbers greater or equal to -2 and less than 6. First, we'll make our number line. All numbers greater or equal to -2 less than 6. I need my endpoints -2 and 6. I want to be greater or equal to -2. So it's a closed dot. I want to be less than 6. Not equal to, so it's an open circle. And here we go. My inequality statement that I would write is -2 less than or equal to x, but less than 6. And now my interval notation, I do a very similar process. I'm going to write my endpoints from lowest to highest, -2 and 6. I want to include -2, so we already talked about that. We're going to use a bracket. But I don't want to include 6. So how could I differentiate so I know that 6 is not included? Well, we're going to use a parenthesis instead. So anytime we use a parenthesis, we don't include the endpoint that we list. And this is all numbers from and including -2 up to 6. Everything in between there. And there's a ton of rational and irrational and integers, and there's whole numbers, and there's counting numbers. There's all kinds of numbers between here. We want them all. We're getting everything in there, everything on the entire interval. And again, I'm including -2 with a bracket, and I'm excluding 6 with a parenthesis. Let's talk about numbers greater than 5. I've only got one endpoint now of 5. I don't want to include it, so it needs to be open. And I want to be everything greater than. Well, I've only got one endpoint. I've got a 5. But it's the lowest value on this interval. I'm not going to include it, so I need to put a parenthesis. Well, what's my upper limit? I'm going to go on forever all the way up to infinity. So I'm going to put infinity there. Well, would I use a bracket or would I use parentheses for infinity? What we have to do is realize that infinity is a concept, not a number. So I can never actually equal it. If we can't equal it, we need to use a parenthesis. So we need to always remember when we're using interval notation and infinity, we always use parentheses with infinities. Always. Now let's look at rational numbers from 1 through 3. Now again, we're going to go from 1 through 3. It sounds very similar to the first one we did up here. We've got our number line here. We've got our endpoints. We're going from 1 through 3. And we want everything in between it, but we only want the rational numbers, not everything between it this time. So there are irrational numbers in here we want to exclude. But where are they located at? Well, we can think of 1 as square root of 2. That's fine. That's in there. Square root of 3 is in there somewhere. But we don't know exactly where all of these irrational numbers might be. It's not a solid interval. It's a very broken interval that has so many breaks in it, there's no way we can accurately represent it. So we can't do this here. We need to have another notation to compensate for for these breaks in this interval. Now, could we do it with roster notation? We couldn't do it with roster notation either, because there's so many rational numbers between here that we couldn't list them all, and there's no process or pattern that we could follow to capture all of them in there on a roster either. So we need to introduce set builder notation. Now, this looks a little funny at first, and there is a little bit to it, but it's really not that difficult, so don't let it overwhelm you. When I talk about set builder notation, I'm going to start with a brace, open it up with a brace right here, and I'm going to write down a variable. I can write any variable, but typically we're going to use x. What this opening means is the set of all numbers x. So the set of all numbers x. And I have another symbol here, this straight line. We read that such that. So what we're saying is all numbers x, every number x, such that, and then over here we're going to put some conditions that have to be met for it to be in this set. Here are my conditions. Alright? The conditions to be in this set is that it has to be between 1 and 3. 1 must be less than or equal to our number, and our number must be less than or equal to 3. So it needs to go from and including 1 up to and including 3. But we put a second stipulation on it. Our number has to be an element of Q. And if you remember, Q is the abbreviation for rational numbers. So our number has to be an element of rational numbers. So let's try and look at numbers from 1 through 3 with set builder. The nice thing about set builder is we can write pretty much anything we want to using it. It's going to be a pretty standard catch-all. Make that a little smaller. It's going to be a pretty standard way that we could write almost any set of numbers that we're trying to define, because all we have to do is keep adding rules until it's met all the requirements that we want for our set. Some are easier, some are a little more difficult. If we want to look at all numbers from 1 through 3, we would start with a brace, all numbers x, such that 1 is less than or equal to x is less than or equal to 3. And that is all we need to write. Now we can also represent this in an interval notation. 1 and 3. Include my endpoints from 1 through 3. So sometimes we can write things in multiple notations at once. But could I write this in roster? I couldn't write this one in roster notation because I couldn't possibly list all the numbers from 1 through 3. There's too many there, and they don't follow the same kind of pattern to increase. Now let's look at integers from 1 through 3. Well, my setup's going to be similar, x such that 1 is less than or equal to x is less than or equal to 3. But I need to add another stipulation. I need to say and x is an element of, you remember the abbreviation for integers, x is an element of z from the German Zahlen for number. And then I would close my parentheses. So I could write, that could be an interval notation. This is set builder notation. Could I write this, integers from 1 through 3, in interval notation? No, because I only want the integers. I don't want any decimals, so I'm going to end up skipping around and breaking the interval. I don't want everything in the interval, just the integers. But could I write the integers from 1 through 3 in roster notation? Sure I could. Again, I would use my brace. The integers from 1 through 3 would be 1, 2, and 3. So we see that we can write some sets using multiple notations, and some sets we could only write in one kind of notation. Set builder is the most flexible form and one of the most common ones that you'll see, and another very common one is interval notation, and of course we'll see roster notation, but it's not as practical as interval or set builder.